Welcome. Uh, in this course, in this lesson, we are going to be covering DBSCAN. So this is another class on unsupervised learning, and we are going to be looking at DBSCAN, and that means like the full meaning of that is density. Let me not put it here. Let's say DBSCAN.ipynb. Then in the markdown here, excuse me. So here we can go. Just one. Density based clustering, clustering, density based clustering of application. I hope I'm correct. Application with noise. I think that's what it means. It's noise. With noise. Yeah. So we're going to be looking at DBSCAN and how it works and the whole thing in between. So firstly, let's quickly go to our board here and get like a quick idea of what DBSCAN does. So in the last one, we looked at a way of DBSCAN is also a way of doing clustering. So in the last class, the approach that we saw to doing clustering is KMeans, right? We looked at KMeans. We look at KMeans, and we mentioned that with KMeans, what we do is we choose a number of K. And so let's say we have a plane like this, and we have some points on that particular plane. Let's see, we have some here also. So what we do is we begin by choosing a number of clusters, right? And once we choose that, we position the clusters anywhere. So let's say we have some cluster here, we have another cluster here, we have sorry, we choose number of clusters that we want. So we place centroids. These things are centroids. These triangles are centroids. So basically what we do is we just compute the distance between centroid and data point, and we sum that, average it out, which is something called inertia. And we keep moving these three things, one, two, three, we keep moving it around till we get to the point that minimizes the inertia, that is, that minimizes the sum square of distance between this and this. So at the end of the day, we have our cluster, right? So we say cluster one, cluster two, cluster three. And that is how K-means work like. But this is just like a quick rundown. So the previous video covers it extensively, really, like the idea and the basic calculation behind it. But this is premised on a lot of things. Number one is you are banking on the fact that your data set does not have outliers, right? You're banking on that fact. Like there are no outliers in my data set. No, that's number one. Number two is you are banking on the fact that you have domain knowledge of what the number of clusters should be. Like you have domain expertise of what your number of clusters should be, which in my experience is not usually the case. But there are cases where you have that expertise, the range or the ideal number of K. But sometimes you don't know, that's one. Then two, sometimes you have very large data set with outliers, with noise, and you need something that can really, really model that nicely. And that is where uh DBSCAN comes in. So how does DBSCAN works? Now, DBSCAN actually does this clustering with respect to three things. So, and they are like really, really important concepts in DBSCAN. So, number one, the first thing is something called epsilon. I hope my spelling is correct. Epsilon. Number two is something called mean samples. Mean samples. Then we have another term called core point, and We have another one called border point, and we have a last one called noise or outliers, outliers. So what is epsilon? So you can think of epsilon as if we have a close. Okay, let's actually use this thing that we have here. So I'm just going to click on this instead of drawing multiple. I'm going to click on this. Let me click out and see if I can choose that. Can I? I will have to move this out and click on this one, delete it. Then might have to move this out soon. That's a lot of work. I should have just cleaned it. Then move this out too and delete it. I can maybe move this back in. I apologize. This is a lot of work. I should have just cleaned it. But yeah, we're done. So yeah. So the first thing that happens is this. So what's an epsilon really? So let's say this is like the cluster, right? And this is me explaining this thing in reverse a little bit, but you are going to get the point. So let's say this is the um cluster, right? The circumference of the cluster. So you can think of epsilon as the allowable distance between the farthest point, that is the farthest data point, to the circumference. I don't know if that makes sense. So let's say between these two, let me put one more point here. So this is another, let's say this is another data point. So if this is another data point, now if you agree with me, you're going to see that this particular black one is the farthest to the circumference at every angle. So if you go like if you compute the radius, like you go like this all around the circumference, you're going to see that this place is the farthest to um the circumference. You might be thinking, well, is this one because well this one is very far from this place, but no, it's really close to this place, right? So now epsilon is now we are now saying the data point that is farthest to this circumference here should not be more than, let's say, let's say we say 1.5 unit. That is the difference between this place and this place is 1.5 unit. Now every other data point that must fall within this cluster must not be more than that 1.5. That is what epsilon means. So it is basically like the radius of neighborhood around a point, around a core point. Now, what's a core point? Core point is that particular data point that bears the epsilon rule. So that particular data point, this black one, is the core point in this case. That is the farthest data point to the circumference. That's the core point. Now, another one is the mean samples. So the mean samples is straightforward. The minimum number of data points that must belong to a cluster before we call it a cluster. That is, you can have a core point, have all of the other border points, all of the other data around it. If they are not enough, let's say we say mean sample is 3. Let's say mean sample is 4. It means all of this thing that we did is rubbish because then we don't have up to 4 data points. So we cannot call any of them a cluster, right? So that is what mean sample mean. The minimum number of uh, data that you need around a core point before you can call it a cluster, and that includes the core point also. But you are going to see it very well shortly. So then we have the border point. Like I said, if this black one is the core point, then the other data here, they are border points. That is, they are within the neighborhood of the core point. So that's why we call them border points. Then noise outliers are, points that, they belong together. They are within the same neighborhood, but they don't fulfill these mean samples criteria. That is, they are not enough for us to call them a cluster because they don't have the required number of samples. So that is um, noise. So again, you can think of radius as the minimum points, and you can think of epsilon as the radius of neighborhood around epsilon, like the radius of neighborhood around the core point like this, around. Great. Then mean samples is the minimum point required to form a region, like a dense region within a neighborhood of a particular unit of epsilon. Then a border point is all of the points within the neighborhood of a core point. All of the points within, all of the points within the neighborhood of a core point, but they themselves as they have fewer number of points to be called their own core points to form a neighborhood, right? Then what then noise, you know what noise means? Those places that do not fulfill this mean sample rule. So let's quickly look at a very basic math implementation. So let's say we have this data point uh, x, y, and let's say maybe we have points also, like the points. So let's call this one the points. So it's easy for us. I don't want us to go plot chart again, right? So what do we have here? Let's say we have one point A, point B, point C. This is just to save us from plotting charts E and F. But with these points, we are going to get it. So we can just have maybe 2, 3, 4, maybe 8, 9, 10. Let's put the same thing here: 2, 2, 3, 4, 8, 9, 10. You are going to get the idea. Now, these are our data points. And what we want to do is we want to actually cluster each of these points. So what's the first step? The first step is to choose values of epsilon and mean sample. So we choose values of epsilon and mean sample. So we say, let's say epsilon equals 1.5, and we can say mean samples equals 3. That is, that radius, the length of that radius is going to be 1.5 units, and the mean sample is going to be, at least before we can call something a cluster, you must have 3 data points. So that's step 1. You choose these 2 values. Now, what is step 2? Step 2. So step 2 is going to be to pick a point. Let's start with point A, and then we are going to now find its neighbors. We are going to try to compute its neighbors. Now, if we are able to find neighbors within this epsilon, within this 1.5, that their value, that is the distance between point A that we have chosen and point B that we are evaluating, if the distance is less than epsilon, we say that that particular guy belongs to point A. And what are we going to use? Again, we are going to use Euclidean distance. That's what we've been using. So that's going to be root of, let's call it A. Did we use x and y? So we're going to say ax minus bx all squared. This is like Pythagoras theorem. Then that's going to be a, no, yeah, ay minus by all squared. So to save ourselves the time, we can just quickly plug the, I'm going to compute for a few, but let's just write a function that does the job. I'm going to say def get distance, and what we are going to be passing in is a let's pass in a list, or let's just do normal points. So we're going to just say x comma y, the values of x comma y. Then what we are going to return is simple. We're going to return what's that formula again? Formula is a, so we have to go value of a, but we are not only going to be computing for a, so we are going to be computing for several things. So I think it makes sense for us to use um the we are going to say like the points that we're evaluating and the neighbors. And the point comma neighbor We're going to check if that is a neighbor. Then we can come here and say this point is going to be a tuple or a list or whatever we want it to be. So we're going to say that we can import math to make it easy for us, but we can always compute that manually. We can say import math, then we can go math.sqrt. That's how you do square root. So what we are going to now do is we are going to say we are going to open another bracket and say point of zero of zero, excuse me, minus neighbor of zero. That's going to be all squared. So start 2 minus, let me just copy this guy here, Control C, and paste this guy here. And that's going to be point of 1 minus neighbor 1. So basically what we are saying is we are going to pass this, for example, for point A. So if we are evaluating point A now, it's going to be 2, 2. So point of A is going to be 2. Point of 0 is going to be 2. Point of 1 is going to be 2. Neighbor of 0 is going to be 3. Neighbor of 1 is going to be like that. So that is cool. I think so. Nope, it is not. It is actually plus, not minus. Including distance is addition. So we can run that and come here and get, we're going to say get underscore distance. Then we can go, first one is going to be, excuse me, first one is going to be 2, 2, if I'm right. Yeah. So first one is 2, 2, 3, 3. So if we run that, we have 1.414. And what does 1.414 means? If you check, where is it? If you check our stuff here, this place, our epsilon is 1.5. So the distance between our point A and point B is 1.414. That is less than 1.5. What does that tell us? It means that point A is very close to point B. So we can do it for every single other one. So we can actually make this nicer by getting a decision. So I'm going to come here, make this Control X, come here and say distance equals this. Then now again, I must say this is not DBSCAN. If you are following the whole explanation, you understand. This is me just explaining. This is not how we like do DBSCAN standard. It has already been packaged for you in scikit-learn. I'm just trying to like help you understand how it works. So we are going to be returning with a decision. So we are going to say true. We are going to be returning true or false, right? So we are going to say uh, we are going to be returning either true or false. So we are going to say verdict. Let's call it verdict. I'm going to say true if, then let's add value of epsilon here. So value of epsilon is going to be some float, and neighbor is going to be a tuple. Points also is going to be some tuple. So I'm going to say verdict equals true if EPS, if distance is less than EPS. Then we are going to say else false. Then we are going to return verdict. Now, in this case, we are checking between A and B. So if we run that and see, we have an error. It says get distance. Oh, we are missing epsilon. So we'll come here and pass in 1.5 as our epsilon. So if we run that, it says true. That is, A is within distance of B. Is that right? A is very, very close to B. We found that. Let's check if A and C are close. So we're going to come here, and if you check C, C is 4 comma 4. So this is going to be Control Z, Z. So this is going to be 4 comma 4. And if we run that, it says false. I think the next one is, so that means C is not within this epsilon row of B. So you already know that D also will not be. D is, I think, 5 comma 5. No, 8 comma 8. D also will not be. So there is no point in checking that. 8 comma 8. But let's just check it and see. It's also going to be false. So it means that at the end of the day, A only has 2 points around it. A only has how many points? 2 points. So I'm going to say A, the points around A, they are A itself and just B. So those are the 2 points around A. Now, don't forget, we need to check how many minimum sample do we need to have for we to call something a cluster? 3. How many do we have here? We have just 2, just A and B. So we cannot call A core point, right? It means A cannot form the center of a cluster. We cannot call this A and B a cluster. So what do? We keep checking. So we can check for B now. So we can go, the next point that we are checking is point B, and that's going to be 3 comma 3, and we can start with 2 and 2. So we first check for 2 around it. What do we have? It says true. So for point B now, let's start for point B. For point B, we know that A is close to it. Good. So what's the next one? I think 4 comma 4. 4 comma 4. True also. So it means point C is also close to it. So B itself is going to be there. So point C is also close to it. Cool. The next one I want to check is 8 comma 8. Come here and check 8 comma 8. Is 8 close to it? False. So it means others are going to be 9 and 10 also are going to be far from it. So in this case, is B a valid um, core point? Yes, it is. Why is it a valid core point? Because it fulfills both 1.5 epsilon, that is, each of these guys are 1.5 epsilon away, and that is, they are within the neighborhood. And lastly, we have minimum sample of 3. So this is less or equals to 3. So that makes it a valid, that makes B a valid cluster. So we already have a cluster now, cluster A, B, and we have a valid cluster that contains A, B, and C. So we do the same for, you get the idea now. We do the same for which one again? We do the same thing for 4, and we check for 2, 3, 8, 9, 10, on and on and on and on like that till we have all of our clusters perfect. We've drawn all of the circles, and then we can now evaluate and see um, how everything comes out. And for every particular point that do not really that do not really fulfill these two rules here, we are going to see that those points are not a cluster, they are noise points. They are noise points. So that is that on the simple idea behind DBSCAN. So let's look at the scikit-learn implementation. Like I said earlier, this is just an helper function. So yeah, let's get into writing the code for that. So as usual, we're going to import pandas. We're going to import pandas as PD for numpy np from scikit-learn dot cluster import DBSCAN from scikit-learn dot dataset. Let's import that same load iris dataset. I'm going to say from, we can, import cborn as SNS, and we can also import matplotlib to pyplot as plt, pyplot as plt. So yeah, we can just go here and get our data. I'm going to say data equals load underscore iris as frame. It's going to be equals to true for data, and we can do data.add and see our data. So without, any special ado, this is a clean data set, which is something you rarely find in real life scenario. But like I always see over the course, there is a dedicated video on data cleaning, data wrangling, data visualization. And the reason why we are jumping into modeling straight is because that is the core of the lesson, and we don't want the lessons to be too long so that we can actually focus on what is important. But in real life, you are going to have to clean your data, visualize it, know the data like the back of your hand before you even get to modeling. So I'm going to say model equals DBSCAN. And the first thing is epsilon. So let's say we choose epsilon of 1.5, or let's do 0.6. Let's start small. And we're going to have mean samples. Let's say mean samples of 6 also. And every other thing is cool. We can leave it as it is. And this particular thing does not take random state because it recursively goes through all of the combinations exhaustively, like it's going to search everything. So, and you can also change the way you do your distance. So if it is Euclidean distance, every other distance that you want to put there. So the next thing that we can now do is we can say model dot fit. We're going to be fitting data. Then we can say preds equals model dot labels underscore. Then we can print out preds. So if we run this, what do we have? We have how many clusters? Just 2 clusters, and you're going to see these negative ones. So these values of negative ones here, they are outliers. They are noise points. They are noise points, and the output of this clustering actually returned just 2 clusters. And we can visualize this by, let me import plotly. I'm going to say import plotly dot express as px. So I'm going to put the output on a 3D plotly chart. So I can say px dot scatter underscore 3D is a data underscore frame. That's going to be equals to data. I can say x equals to, x is going to be equal to sepal length, I guess. I don't know the spelling again. So we can just come here and get data dot columns. Data dot columns, and can copy this like this and paste it here. Then we can go x equals this, y equals this, z equals this, and we can come here and say color equals breadth. So if we run that and see what the output is going to be, we're going to get an output that shows the 3D chart of our data. That's taking too long, but it will come up at some point. Yeah, so we are here. Now, if we check this now, okay, hold on. If we check this, let me slide up a bit. Now, if we check this, you're going to see that we only have 2 clusters. Cluster 0, I guess. Yeah, cluster 0 with that pop. I'm very terrible with colors, so maybe I don't know what color this is. Maybe red, but that's not red. Then this yellow one. Then these blue ones, they are outliers. And you cannot consider outliers as clusters. They are not, because outliers are not outliers the same way. They are outliers for different reasons. So yeah. Now that is our cluster. Now, how do we now actually evaluate this thing? Because we cannot settle on this being the perfect cluster, because if I change this to like 0.9 and change this to 5, I'm going to have a different outcome. It is still 2 with no outliers. To the best of my knowledge, with no outliers, still 2 clusters with no outliers. So if I should rerun, I've rerun this, we are going to see, can you see? 2 perfectly separated, no outliers. That's interesting. If I should bring mean, if I should bring epsilon all the way down to like 3, at some point you're even going to get errors. Like it's going to tell you like you don't have, can you see, like now we have 3 categories, like 3 groups, and lots of outliers, like lots of outliers. So now we need to actually know what values of epsilon to choose, and how do we even evaluate the how do we evaluate the performance of our model. So we use something called silhouette score, and let me come here and add evaluation model evaluation with silhouette. I don't know how to spell that. I guess this is correct. Silhouette score. So how does that work? How does silhouette score works? So a silhouette score works by um, um, comparing the distance between. Now the sklearn implementation of silhouette score is actually the average of all of the silhouette score. So silhouette score is not something that you compute for the general data set at once, but we compute it for each of the data points. Then we now actually take the overall average. So I'm going to show you just the simple arithmetic behind it. So I can say from, let's import it firstly. From sklearn dot metrics import silhouette score. Yeah, that is cool. So if we run that, we can, oops, that's too much. Let me um, maybe just rerun it and then go to the next line. Okay, cool. So let's come to our board again and try to understand how silhouette score works. So how do we compute silhouette score? So we compute silhouette score with this particular formula here. Let me move this up a bit so you can see. Um, excuse me. How do I do that? Okay, great. So we can say S is going to be equals to, so we are going to have 2 points, point A and point B. So we're going to say S goes to B minus A all over max of, like, the maximum between the two of them, B comma A or A comma B, any which one. So what does it mean? Firstly, what does A mean? So A is the average distance. I mentioned earlier that you don't compute silhouette score of the entire data set at once. Like, this is not the silhouette score of the entire data set. It's basically the silhouette score. We can basically just put IASF if you want. You can say SI, something like that. So it's the silhouette score of a single point, So what does this A mean? So A is the average distance from the point that we are considering to all other points in the same cluster. Basically, let's say this is our cluster. Don't forget, we use KMeans for this, but let's just assume that we used what do you call it? Let's assume that we used DBSCAN. So if we are computing the silhouette score for this black guy here, think I'm offline. Let me try and reconnect. So if we are trying to compute the silhouette score for this guy here, this black guy here, dark black guy is going to be our A, right? The position A. Now, what is so the distance between the points that we are considering, the average distance between the point that we are considering from all of the other points within its own cluster, like within this same cluster here, the distance between this guy and this guy, the distance between this guy and this guy, the average distance is our A. So it measures how well that point, that our black point, this black point here, how well it is assigned to its own cluster. What right does it have to be in that cluster? We measure it. Is it really supposed to be here? So we compute the distance. That is A. A, again, the average distance between this guy and all of the other points within this cluster. So the second one is B. This B here. So B is going to be the average distance from the point, that is the points that we are considering, to all the points in the next closest cluster, that is the nearest neighbor. So let's say this is the next closest. Where's my mouse? Let's say this is the next closest cluster. So I mean the common sense behind it is, well, if this is wrongly put here, then maybe it should be in the place that is closest to it and not where it is currently. So what we are now going to do is we are now going to compute the distance between this guy here and all of the data points here. So this is us assuming that this is the next closest cluster. So this measures how well separated the points are, that is from this particular place to the next separated cluster. So a larger value of B, like if B is very large, that is the average distance between this guy and all of the guys here. If it is large, it means that okay, it is well separated. It probably should not be there. So we've put it in the right place. Then we now divide that all over max of B over A. And silhouette score is actually a value. So we can add that here. We can see silhouette score, excuse me, the board is connecting here. So we see silhouette score is actually, it lies between -1 less than or equals to S less than or equals to 1. So S is between -1 and 1. It's a value between -1 and 1. And anything greater than, we say S, excuse me, S greater than 0.5 is what we want, generally good. And what does that mean? What it means is, if we have something like S greater than 0.5, we consider that as very, very good cluster if S is greater than 0.5. And what does S existing in the negative axis, what does it tell us? It tells us uh, two things actually. Excuse me. Yeah, it tells us two things. So the first thing that it tells us, if S is close to -1 or even exists in the negative spectrum, is that, oh, before I mention that, let me say that we are going to get values of S for each of the data points, then the overall silhouette score that we're going to be getting for the clustering that we've done is the average of all of the individual silhouette scores of each point. So good. Now, if we now have a value of -1, it means that the point might be assigned to the wrong cluster. That is, you have so many points bearing negative values, 0.6, negative 0.6, negative 0.7, like that. It means a lot of your points are wrongly clustered. They are not where they are supposed to be. Good. Now, a silhouette score that is very close to zero, whether negative or positive like that, it means that the points are, near the decision boundary between two clusters. That is, they are very close. They are not well separated. They are very close to the decision boundaries, the boundaries where we are actually splitting into different clusters. They are too tight. Then the last one is, if S is very, close to +1, which is what we want, anything greater than 0.5, it means the point is well clustered and it is much more separated. That is, the distance, like the average distance between the points in its own clusters, which is A, is much more smaller than the point in the next closest cluster. So basically, the greater the value of S is in the positive axis, the better. And that's what we are going for. So that means you can always come here. For example, we can come here and we've imported it. We can say silhouette score like this. And what goes into silhouette score is our X. So our X is going to be our data, and our labels is going to be threads. So if we run that, it says 0.68. So this is not bad. You probably could get bigger values for higher values for this. So this is for 1.5 comma uh, that is epsilon of 1.5 mean samples of 4. So you could search through different values. You could do that within an hyperparameter tuning, or you could do that by just writing your basic for loop. So that is how we evaluate. So again, let me make this smaller so you just see a different value of epsilon. So if I should come here and do 0.3 here and make this one 3. Right. So you see a lot of it got up to 7 clusters with tons of outliers. So let's go into our silhouette score and see if that how that comes out. So if we run that now, can you see it got really bad 0.03? And this is what I explained about something being close to zero earlier. What does that mean? It means a lot of the points are near the decision boundaries, like they could have just fallen to the other side. So that means you have too many clusters that are not supposed to be clusters, they are just supposed to be bounded into one. And if you visualize that in here, and let it come up. Once it comes up, we're gonna see coming. Yeah. So if you actually visualize the chart, you're going to see that a lot of things are overlapping. Can you see? A lot of points very close to the decision boundaries. Everything is just, for example, this. Let me move this around very well. This particular blue here could have just easily fallen into this place, right? So it means our this score very bad. So yeah, that is how clustering works, and I hope it makes some sense from the idea behind it and how to evaluate it. So this is a much more better clustering, a little bit better than what we had earlier. So I just changed the value of epsilon to 0.5, mean samples to 4. And yeah, this looks a bit better. And we have 3 clusters. Is it 3 or 4? 3. No. 0, 1, 2 is 3. So we can check the scores here and see. So it's better than the one we had earlier, 0.38124. So that is how we do clustering with DBSCAN. That is the idea behind DBSCAN. So in the next one, we are going to be seeing um, principal component analysis, PCA, how to do decomposition in unsupervised learning. So thank you for joining in. See you in the next one.